All right, well, we want to systematize some of these things we've been talking about. Remember, if we have a matrix H, we can define a linear code, and we can choose H in such a way that makes it easy to encode and decode messages. Okay, so the way we do this is put H in standard form, and these are called standard generator and canonical parity check matrices. All right, suppose we have this matrix H, and suppose that the last m columns form an m by m identity matrix. Now, typically you will have the number of rows is less than the number of columns. So here we're saying the last m columns form an identity matrix. So it's going to look something like this. You're going to have 1, 1, 1, dot, 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 1, and then 0, 0. And then up here you're going to have stuff. The matrix will look like that. So you can easily tell visually whether a matrix is a canonical parity check matrix. It should be immediate. So that means H can be divided into two parts. The first part is going to look arbitrary like this. It'll have all ones and zeros, but it will be an arbitrary pattern. And the last m by m block will look like an identity matrix. Now, you can associate with this something called a standard generator matrix, which is related in a way that we'll see later. Basically, you take this same leading matrix, and instead of stacking it in front of an m by m identity matrix, you stack it on top of an n by n. You stack it below an n minus m by n minus m identity matrix. All right, let me say that again. To get the standard generator matrix, instead of stacking this leading matrix, which is m on this dimension, and it's n minus m. It's m this dimension, and it's n minus m this dimension. Now you can see if I take this matrix and stack it in front of this m by m identity matrix, since this has the same number of rows as this one, then we're okay. Now if I was going to stack this under an identity matrix to get a well-defined matrix, see, this has n minus m columns. So if I stack it under the identity matrix with n minus m columns, it will have the same number of columns, so I can form a well-defined matrix that way. Okay. Now here it says our goal is to show that gx equals y if and only if hy equals 0. So let's digest that a little bit. Gx equals y if and only if hy equals 0. In other words, if I take any vector x, hit it with g, and form a resulting vector, that vector will satisfy hy equals 0. In other words, that's a code word. So if I take any x as any information word, then I multiply it by g, and the result is a code word. This gives us an easy way to generate code words from information words. Now let's work out the dimensions here. Let's see, suppose x is my original matrix, my original code. Now how big must my original code word be in order to create my original information word? How long must my original message word, I should standardize my terminology, call it message word. How long must my original message word be in order to achieve a code word that is of length n? Okay, let's see how that works out. Well, g is going to be a n minus m this way, and it's going to be n minus m this part and m this part, so altogether this is of length n. Okay, so what that means is if x is going to be, so g is n by n minus m, in order for gx to be equal to y, in order to make this matrix multiplication work out, x must be n minus m by 1. Then the result is going to be n minus n by 1. Okay, so my code word has n digits. My message word has n minus m digits. Okay, that's a little different from how we started out at the beginning of the chapter. At the beginning of the chapter, we had a message word with M digits forming a code word with N digits. Here we are changing notation, saying the message word has N minus M digits, and it yields a code word with N digits. Okay, so let's look at this example here. Suppose we have 8 words to be encoded. Okay, these are all of the 3-digit binary words. There's 8 of them. Now he's taking this matrix A. This is the leading matrix in the canonical parity check matrix. Now how would I form a parity check matrix out of this? This is 3 by 3. Now from this information we need to work out what M is and what N minus M is. So we'll have to go up before and see how that works. Notice in the definition of A is a M by N minus M matrix. Now remember, N minus M is going to be the dimension of the information word, and M is a special dimension. So actually the N minus M plus M is equal to N, so that's the length of the code word. So from this information about A, we know that N minus M is equal to 3. We know that M is equal to 3. So that means that N is equal to 6. Our code words are going to have 6 bits in them. Now, in order to have a 6-bit code word, our matrix G is going to have to be 6 by 3. 6 is the dimension of the code word. 3 is the dimension of the information word. And this is the matrix that we are going to multiply by our original information words to get code words. Okay, so we had our generator matrix on the previous page. Here's our parity check matrix. You have the identity matrix, and in front of it you stack this matrix A. Now why is this actually called a parity check matrix? Well, the way it's set up is, look at these bits on the diagonal here. What you get for the first row, for instance, you get the sum of these 2 bits plus this bit is equal to 0. That's what this indicates here, sum of these 2 bits plus this bit. In the second row, you get the sum of these 2 bits plus this bit, which is x5. That's what's expressed here. The sum of these 2 bits plus x6, that's what's expressed here. Now the thing is that that's expressed in this way. What that means is that x4 serves as a parity check on these two bits. In other words, the sum of these 3 bits has to be equal to 0. That's a parity check. x5 serves as a parity check for these 2 bits. x6 serves as a parity check for these 2 bits. Now notice that in each one of these equations there's at most one of these 1, 2, 3 bits. Each one gets exactly one of these bits. So x4, x5, x6 serve as parity check bits for their respective equations. Now, how would we check the null space of the matrix? We have to check all the solutions of these 3 equations. Now, the way to do that, very easy way to do that, is set up a table x1, x2, x3, x4, x5, x6. Now, it turns out that the first 3 bits determine the last 3 bits. For instance, suppose I have x1, x2, x3. Suppose I have 0, 0, 0. Okay? That determines what x4 has to be. If these 2 are 0, then x4 must also be 0. If these 2 are 0, then x5 must also be 0. If these 2 are 0, then x6 must also be 0. Okay? How about suppose I have x1 equals 0, x2 equals 0, x3 equals 1. Well, this x2 is 0, x3 is 1. That means x4 must be 1. Okay? X1 is 0, x2 is 0, x5 must be 0, x1 is 0, x3 is 1, x6 must be 1. Okay? So you can go through this table. You're going to have 8 rows in this table. The next one, 0, 1, 0, etc. Go all the way down to get all combinations of these 3 digits. And these 3 digits will determine these 3 digits over here. Okay? All right, so that's one way to compute the null space. When I finish this, every row in this table will be a solution to the null space of the matrix H. Okay. Another way would simply be to multiply every one of the code words by the generator matrix G. And let's see how that works. All right, let's go back up here to G. G is this one. And we want to multiply this by every single one of these code words. Let's, for instance, take this one, 0, 1, 1. If I multiply G by 0, 1, 1, let's just put here 0, 0, 1. Sorry, I said 0, 1, 1. It should be 0, 0, 1. If I multiply this matrix by this column vector, if you think about it, you're going to do row times column, row times column, row times column. That's how it works. Whenever you do row times column, you're actually going to pick up the last entry in each row. Think about it. Do the first row times column. 1 times 0 plus 0 times 0 plus 0 times 1. All right. The first two really don't do anything because they always multiply by 0. It's only the last one here that gives us some contribution. Now, since the last entry in this row is 0, that means the result is going to be 0. In fact, I can just read the result off of the last column of G. It's going to be 0, 0, 1, 1, 0, 1. So that's going to be a code word. Now, if you think about this, if I multiply G by 0, 1, 0, 0, that's going to be equal to the first column of G. Okay. If I multiply G by 0, 1, 0, that's going to be equal to the second column of G. So what's the conclusion? The conclusion are the columns of G are code words. The columns of G are code words. Easy way to find out what the code words are. Now, that's not all the code words. That's only 3 of them. It turns out, though, that we can get all the code words in terms of these 3 code words that we get by the columns of G. Okay, let's look at see what Theorem 10.7 says. Theorem 10.7 says, let's have a matrix, a m by n matrix with entries in Z2. It's a canonical parity check matrix. That means that H has this form, A, and then the identity. Then the null space of H consists of all x. The first n minus m bits are arbitrary. The last m bits are determined by these equations. Now remember what the dimensions of this are. Okay, the dimensions of A are, let's write that down again here. A was, we had AI here. The dimensions of A were m here. This I is going to be a m by m, and this there you have an n minus m this way. Okay, so actually, if you have this matrix H, and Hx equals 0, what this is actually is each row of H gives us a different equation. It gives us a different inner product with this x. So this H actually represents m equations. Each equation is a parity check bit. The jth equation here is going to be the jth parity check bit in the last block of m bits. Okay, so you'll see how this works when we work certain exercises. Okay, so when you think of the code word, the first n minus m bits, those are called information bits. Those can be arbitrary. You can get any combination. That means there's going to be 2 to the n minus m possibilities for the n minus m information bits, and those determine the check bits. And the first row of H determines the first check bit, and so on. Works your way down like that. All right. Now this theorem expresses the other way of creating code words. Take a standard generator matrix, multiply it by all possible vectors of the right size, and you will obtain all code words in a group code. And this goes through the proof.